All right, so what I want to do now is finish up Hilbert spaces by talking about orthonormal bases. I'm going to prove a main theorem about orthonormal bases for Hilbert spaces, and in another video I'll do applications of this theorem, particularly applying it to Fourier series and applying it to finding an orthonormal basis for the Bergman space. Okay, so before I do anything, I need the following proposition that I'll leave for homework. I don't know if I'll collect it or not, just because, there's so many good homework problems in the book that, I can't assign everything for homework. But this really is a pretty straightforward result. So if we're in an inner product space and we have, I might have actually mentioned this before. So if I have xn converging to x in my inner product space and yn converging to y in my inner product space, then we have this inner product here, xn, yn, converges to the inner product x and y. And the proof is fairly straightforward. Basically, you're going to use the Cauchy-Schwarz inequality and add and subtract something obvious. So, okay, right. So remember last time what we did was we computed the orthogonal projection from L2 of the unit disk to the Bergman space. And as we'll see in a moment, or maybe later on in the video, that we can actually compute the orthogonal projection for basically any nice Hilbert space. Okay, so to start that off, kind of to get a little taste of what's to come, I want to prove the following actually fairly straightforward proposition, which is actually a homework in the book, but I think it's worthwhile to prove. So let's say we have a Hilbert space, and let's say we have a orthonormal sequence. So let's say this is orthonormal, or for short, ON. So what does this mean? Well, it has the, you all probably know what this means. The inner product of EJ and EI, EJ is going to be the delta ij, which is 1, I equals j, 0, otherwise. Okay. Also, let's suppose that we define big M to be the span of this sequence here. And yeah, it's just the usual linear algebra span. So just so that we're all on the same page here, that's the set of all linear combinations of the vectors EJ. And sorry, I should say, right, so we're dealing with the Hilbert space. So script H is a Hilbert space, and this is, an orthonormal set in my Hilbert space, and this is big N here. So I claim, and sorry, if this is not clear, this is a set of all X where X can be written as a linear combination of the EJs. Right, so first of all, it's an easy homework exercise. I doubt I'll collect that M is actually closed, certainly a subspace. So I claim that the orthogonal projection from H to M is given by this nice formula, the usual linear algebra formula. It's X, EJ, EJ. All right, so what is the proof? The proof is, well, let's say this here is P tilde J, for lack of anything better to call it. So we want to prove that it's equal to Px, but we don't know what it is. And P here, of course, is the orthogonal projection from H to M, if I didn't say that already. So let's define Px, P tilde X to be this formula here. All right, so I claim that the following is true. And I claim that X minus P tilde X is in the orthogonal complement of M. And why does that prove? Why does that finish the proof if I can verify this claim? Well, this is just an application of the uniqueness of decomposing your Hilbert space element as something in M and orthogonal to M. So in particular, if this is true, then X equals P tilde X plus X minus P tilde X. Well, this is trivially in the span of, and of course I should say, not that it's really obvious, but this is all X and H where this is true. But anyway, the P tilde is obviously in the span of the EJs. That's trivial. Okay, so this is obviously in M. So if the claim is true, this is in M perp. And remember, there's only one way to write X as something in M and something in M perp. And that is, that only way to do that is if P tilde X equals Px, and well, X minus P tilde X has to be Q of X, which is just X minus Px. So we don't really care about that. This is basically it. That's what we wanted to. That's exactly what we wanted to prove. So let's prove the claim. Yeah, and obviously it's enough to show that X minus P tilde X inner product EJ is 0 for any J 1 through N. Why is that? Well, let's see why. So I want to compute this here. So let's call this star, whatever it is. Well, star is just x, x ej minus p tilde x ej. Well, what is p tilde x? P tilde x is given by this here, so let me erase what I had before and write in for p tilde x the sum. Maybe I'm gonna have to make this a little bigger. I think I could fit this in. So j equals 1 to n x ej ej. I'm just going to move this over a bit. Okay, so just use linearity, xej minus j equals 1 to n, and you should see where this is going, xej, pull this scalar out, and then use, or the fact that we have an orthonormal basis. Sorry, that doesn't make sense. This should be, let's say, little n. Sorry about that. Yeah, that makes much more sense. Right, so yeah, that. All right, so this is En, Ej. Well, remember this here is 0 if n is not equal to j, and if it is equal to j, it's 1. So this obviously collapses to, well, 0. Okay, so this has a very useful consequence called Bessel's inequality. And it's the same Bessel as Bessel functions if you've taken an engineering math course. I think Bessel came up with this in the context of Fourier series. I actually don't know the history off the top of my head, but what's Bessel's inequality? Well, if I have a sequence, not necessarily finite, an orthonormal sequence, and the meaning is exactly the same. We just have a countable number of elements in my Hilbert space where exactly what I'm circling in purple, or I think this is purple, whatever color this is, exactly where this is true. Okay. So yeah, this is orthonormal. And we have some, let's say, little h. I guess I'll use little h for something in the Hilbert space rather than x, whatever. Okay, then we have the following is true. This sum here, h, e, j, inner product, converges, and moreover, it's less than the norm of h squared. So what's the proof? Pick some big N, some natural number big N. Let's say M is exactly what it was maybe 5 or so minutes ago. The span of the EJs. Well, in general, we don't know if this, certainly in general, the span of all of these might not necessarily be closed. So let's just take the span of n of these. I should maybe label this as EJ, if I have EJ here, that. So this is a closed, like before, it's a closed subspace. So, right. So we have from the projector theorem, if P is the orthogonal projection from H to M, that the norm of H squared is a norm of, well, it's really from Pythagorean's theorem, plus the norm of QH squared, which remember Q is at H minus PH, but whatever. So this is certainly bigger or equal to, this is non-negative, the norm of PH squared. And all we need to do now is figure out what that is. So we're going to use the facts of about projections, about the orthogonal projection rather, that we talked about in the last video. So, well, the last two videos actually. So, well, always, this is the inner product PH. This is, I can bring this, maybe I'll bring this P over here. It doesn't matter which one. I can always bring a P over. I believe we actually did this P here over. So I'll do that. So it's H, P of PH. But we know what that is. PH is an M. And remember, P of anything in M is just itself. It's one of the properties of this orthogonal projection. So this is H, P, H. And you can just, remember, you can remember what PH is. It's this sum here. P equals 1 to N. H, EJ. So this is obviously just pulling, just using linearity. This is, well, just H, EJ, inner product times H, EJ, inner product conjugate, which is the modulus squared. All right, so, right, so what do we have here? We have this quantity here. For any big N whatsoever is less than or equal to the norm of H squared. So now all you do is let big N go to infinity. No harm there. Sorry, it's big N. All right, so just a quick comment, not terribly important, but in Bessel's inequality, completeness is not necessary. I'll explain why in a second. Well, let's say we just have, let's just say we have an inner product space. I guess I'll still use H, even though whatever. And let's say big X is an inner product space, not necessarily complete. So IPS for inner product space. Well, we can just cook up pretty trivially a Hilbert space, being just a span of, well, the EJs and H. And let's just say M is, just as before, span of the EJs. Okay, so everything I just, yeah, so just apply Bessel's inequality to M and H. Certainly little h is in this Hilbert space H. So you get exactly what we had before, that the, that the sum here inner product H EJ squared is less than or equal to the norm of H squared. And again, let n go to infinity. Okay. And again, I'm just using Bessel's, basically the proof of Bessel's inequality with respect to this Hilbert space. Little h is certainly in this Hilbert space. M is a closed subspace of this Hilbert space. So everything that I did before works. So, right. All right. So, want to make a definition. And it's a definition of an orthonormal basis. It might look a little weird, but we're going to show that it kind of leads to what you would expect an orthonormal basis to be from your undergraduate linear algebra. So by definition, an orthonormal basis is a maximal, in kind of the usual sense, maximal orthonormal maximal orthonormal set. I'll call that script E. And what does maximal mean? So if you have some larger orthonormal set, and when I say orthonormal, I mean everything, well, if you just have, let's say, x and y in script E, then either, if x is not equal to y, then the inner product is 0. And if x equals y, the inner product is just 1. So everything in script E has norm 1, and everything is pairwise orthogonal. You take any two distinct elements in script E, take their inner product, it gets 0. That's what it means to be an orthonormal set. So yeah, if you have anything larger, well, basically there is nothing larger. If you have something, that's a superset of E, then they have to be equal. So there does not exist a larger orthonormal subset of your Hilbert space. Okay. All right. So one more definition before I state the main theorem here. So we say a Hilbert space H, and here H is a Hilbert space. Actually, I mean, this applies in more generality for an inner product space, but we'll talk about that later. And later on, we'll talk about the existence of an orthonormal basis for any inner product space whatsoever. Okay, so H is a separable Hilbert space, By definition, if it has a countable orthonormal basis, let's call it EJ. Okay, so a homework, which maybe I'll collect this. I probably will. H is a separable Hilbert space if and only if, well, H is separable. Sorry. And what do I mean by that? It's separable as a metric space. So there exists a countable dense subset of my Hilbert space. Okay, so from that perspective, it's a good terminology here saying H is a separable Hilbert space if it has a countable orthonormal basis. And I should emphasize that virtually every single practical Hilbert space you'll ever deal with is separable. I mean, in a lot of books, they only, the authors don't even want to look at non-separable Hilbert spaces because they're so pathological that there's no point sometimes. Okay, so let me prove the following theorem, and yeah, in the next video I will do some applications. So the theorem is as follows. If H is a Hilbert space, sorry about that. I've done a good job withholding my urges to write in cursive. So I gotta hold that back for the whole semester. But so if H is a Hilbert space, sorry. So if H is a separable Hilbert space, and we have EJ being orthonormal, again, same as orthonormal definition, same as at the very beginning. Just exactly this here is true for any I and J. Then the following are equivalent. A, this is an orthonormal basis. It's a maximal orthonormal set of my Hilbert space, subset of my Hilbert space rather. B, for any element in your Hilbert space, all of these equal 0. And obviously I'm just indexing this by the natural numbers. Index it by any countable set. Well, this implies that H equals 0. C, I don't feel like writing for any H each time, but for any H in your Hilbert space, you can write H in terms of your orthonormal basis. H, EJ, EJ. 2 more, D, for any H in your Hilbert space. The norm is given by this sum here. And last but not least, for any H and G in your Hilbert space, you can write the inner product in terms of your orthonormal basis, HEJ, complex conjugate G, EJ. Okay, right, so how are we going to prove this? We're going to prove that B implies C, implies D, implies E, implies B. Can make a little song out of that. And then we're going to prove that A is equivalent to B. All right, so let's do B implies C. So, right, I want to, take some H in my Hilbert space and want to show that I can write it as follows. So let's first of all show that this sum exists as an element in my Hilbert space. And when I write this, I mean convergence of this infinite sum is in the Hilbert space norm. So yeah, let's prove that the sum even converges to something in the Hilbert space. Let's say Sn is the partial sum of what we want to look at. All right, so let's prove that it's Cauchy. We're dealing with a Hilbert space. If it's Cauchy, the partial sums, then we will have convergence to something. And let's assume without loss of generality that n is bigger than m. So we could just use Pythagorean's theorem. There's really not a whole lot to this. So this is j equals m plus 1 to n. Yeah. Right, so use Pythagorean's theorem and the fact that we are dealing with an orthonormal set, we have that this is going to be equal to j equals m plus 1 to n h ej modulus squared. And this converges to 0 as n and m converges to infinity because, well, in particular, this sum here, HEJ, modulus squared, converges. I mean, I don't even care that it's less than or equal to the modulus A squared. I just care that it converges. Obviously, this is not infinity. Okay, right, so that means that we have that this defines a something in my Hilbert space. And convergence is in my Hilbert space. All right. All right, so let's say H tilde is equal to H minus whatever this is in my Hilbert space. Okay, so right, so what I want to do is I want to prove that H tilde equals 0. If H tilde equals 0, then trivially I have C is true. H is the sum here. Right, so how do I prove H is 0? Well, I'm going to assume B is true, and I'm going to prove that for each J, this inner product is 0. That'll imply that H tilde is 0. And sorry, I'm applying that to H tilde, not to H. Certainly not going to be true for H here, because H is just some arbitrary element. Okay, so, right. So H tilde En for each N. Actually, yeah, I mean, I'm going to use J for a sum. So maybe I should use M. I mean, it doesn't really matter. Yeah, I'll use M. I just have to prove each one of these is 0. So what is this? Well, so remember from the very beginning, I wrote down a little proposition here that I said is homework right here. Now I'm going to use it. Actually, I'm just going to have one of the, like basically the yn being a constant sequence. So in particular, xn inner product y converges to x inner product y. So here, my y is just em. Okay, so this is going to be h minus the sum here. J equals 1 to n. Up a bit. H, E, J, E, J. Inner product EM. Well, just use, all you have to do here is use linearity. And the reason why I want to do this is it's kind of murky to use linearity with infinite sums, because there's nothing in the definition of a Hilbert space that says you have anything resembling linearity with an infinite sum, really. So anyway, yeah, this gets rid of any murkiness. So this is going to simply be, well, H, H EM minus the sum here, J equals 1 to n, H EJ, EJ, EM. Well, again, J has to equal M, otherwise this is 0. And if J equals M, this is 1. So it's just HEM minus HEM. Oops, H inner product EM. And again, by B, because we have this as true, for every single M whatsoever, this implies that, H tilde equals 0. So again, that means exactly what we want to prove. H is this sum here. So that takes care of B implies C. That's really probably the hardest part. Not that that was particularly hard, but okay, so let's do C implies D. That's pretty straightforward. So H is this limit here. Remember, Sn was just this here. And this is a little messy. Like that. That's a little better. Right, okay. And the assumption again in C is that this convergence is in my Hilbert space. It's convergence in norm. So we have convergence in norm. And remember, we proved, forget if I proved it or I left it for homework, either way, we have the norm of H, therefore, is going to be this limit here. Well, as often with Hilbert spaces, norms don't really help me that much. Norm squareds help me. Okay, right, so just again, remind you of what is inside this norm. J equals 1 to n. And so just use Pythagorean's theorem. We get, I'm not going to try and squeeze it here. Well, this is just equal to j equals 1 to infinity. Times this, sorry, lost my train of thought there. It's just this sum here using Pythagorean's theorem and the fact that we are dealing with an orthonormal set. Okay, so now let's do D implies E. And I'm going to not go into a lot of details here. This is quite messy. And as one of my professors when I took a Riemannian geometry course aptly said, the details of this are best done in the privacy of one's home. Right, so remember let's see what D, just remind you what D implies E is. It's pretty straightforward, it's just kind of messy. Basically, we just have to go from norms to inner products. How do we do that? And I should say that by Bessel's inequality, what I'm circling is perfectly well defined. Using the Cauchy-Schwarz, you can just smash in absolute values, use the Cauchy-Schwarz inequality, and actually, you know, this sum here in modulus is less than or equal to the norm of h squared times the norm of, the norm of h times the norm of g. Because remember, this is what Bessel's inequality says. So there's no ambiguity in whether this sum converges or not for two elements, h and g, in my Hilbert space. It absolutely does. Okay, so yeah, let me outline this, and I'm not going to collect this. If you so desire to fill in all the details, sure. I'm not going to say it's the best use of your time, but certainly if you have nothing better to do, I suppose you could use your time. There's worse ways to utilize your free time. Okay, so, right. So one can check that the following is true. And this is called the polarization identity. And this is in the book on page 12. It's true for any inner product space. It's just a direct calculation. There's no subtlety whatsoever. So we can write the inner product in terms of a norm. You just literally expand everything out. So it's a norm of h plus g squared minus the norm of h minus g squared plus I times h plus I g squared norm. I is just the usual I minus I times h minus ig norm squared. Yeah, just, I mean, for example, what do I mean by expand things out? Well, this one here is h plus g, h plus g product. So just use linearity, do this for all three of these here, and that's basically it. Make that a minus sign. All right. Right. So what I want to do now is use D for all four of these. Okay. So what is this going to be equal to? Let me get rid of this. So this is 1/4 times this sum here. This is going to be a challenge to fit, so I have to move it over here. Sorry about that. Right, so this whole thing here is going to equal 1/4. If you go back, yeah, like I said, I'm just applying D to all four of these. Combining it into one sum. So it's h plus g ej squared minus h minus g ej squared I h plus I g ej squared. I'll fit it down here. H minus I g ej squared. Okay, so now what you do is, I'll just show you the rough idea for this one here. You just expand this, or basically not really expand it. You write this as h plus g ej times, ej, or yeah, you can do it like this, ej h plus g, and use linearity, do FOIL, write out the terms that you get. Do the same thing for all four of these, and when all the dust settles, you're left with nothing. Sounds very philosophical and nihilist, but you're left with nothing, but you're left with something, and that is h ej, oops, inner product g ej complex conjugate. All right, so yeah, like I said, not very enlightening, all these details, but if you want to do it, sure, can't argue that. Okay. Right, so now let's do E implies B. We just took care of D implies E. Okay, so right, so let's check that B is true. So what do we have to do? Let's assume that h ej equals 0 for any natural number j. All right, so let's just actually apply E with G equals H. That's it. So apply E with G equals H. E is saying for any H and G, this is true. Yeah. This is going to be equal to J equals 1 to infinity, H, E, J, H, E, J, complex conjugates is 0. Well, the norm of H is 0 implies that H equals 0. And that's exactly what B is. B is if what I'm circling is true for any J, then H is 0. So I guess I should circle or put in a rectangle rather. Oops. Didn't want to do that. Sorry about that. If this is true, then H is 0. All right, and I'm running out of space in my Zoom whiteboard. Gotta probably figure out a better option. Anyway, so yeah, what we've proved is B implies C, C implies D, D implies E, and E implies B. So all of those are equivalent. So we've just proved that everything here are all equivalent. So now I just want to prove that A is equivalent to B. And that's pretty easy, actually. There's really not all that much to that. So let's assume A is true. Okay, so assume A is true. So again, what do we want to prove? We want to prove B. So we want to prove that if this inner product here in circled blue is 0 for all J, then H is 0. All right, so if H, E, J equals 0, yeah, and let's assume actually that H is not 0 in norm. Or rather, let's just assume same thing. H is, and sorry, just to clarify, this is assume this is true for all natural numbers n, but H is not equal to 0. Then, right, then what do we have here? Well, we have a violation of maximality, and that's, you know, it's a violation of maximality. There's not much more to say than that. Because what do we, well, if we just literally take this here union, not H, but H over norm H, then this is an orthonormal set. Everything here in this union has norm 1, and everything inner product with something else is going to be 0 if that something else is not, if the two elements are not equal. In particular, you take EJ inner product EI for I not equal to J, you get 0. take EJ inner product any of, H over the norm of H. For any J, you take the inner product, you get 0. That's exactly what this is saying. We should do it in blue, but whatever. Oops, sorry about that. So this violates maximality. So in particular, H equals 0. So that means A implies B. And let me finish this video. This is getting quite a bit long. With B implies A proof. So maybe I should have put that here. Whatever. Right, so let's assume B is, so what I'm going to do is assume B is true. All right. So if this here is not a maximal orthonormal set, then pick H in my Hilbert space where particularly H is not equal to 0, where what I'm writing down here is a orthonormal set. All right. Well, this is an orthonormal set here. What does that mean? That means and sorry, I meant to say that I won't write it down, but H is not any of these EJs. So we're assuming this is not maximal, so we're picking an H, where H is not any of these EJs, and this union here is an orthonormal, not an orthonormal basis. This is just an orthonormal set. So this is orthonormal. Sorry about that. All right, well, anyway, if this is orthonormal and if H is not any of the EJs, then that means H inner product EJ equals 0 for any J in the naturals. So that implies H is 0. And that's a contradiction. That's we assumed that H is not equal to 0. So in fact, this has to be maximal. Thus, this is indeed maximal. And that finishes the proof. Right, so in the next video, I will show that for any orthonormal basis in a separable Hilbert space, this formula here holds true when you sum J equals 1 to infinity, or rather this is true. Where you have rather, where Rather, if you have a separable Hilbert space and you have an orthonormal basis for a closed subspace of your Hilbert space, which is itself a Hilbert space, then the orthogonal projection is just given by the sum here, j equals 1 to infinity. I'll prove that in the next video, and I'll apply everything we've done so far to the Bergman space, write down a very natural canonical orthonormal basis for the Bergman space, and just remind you what we did in harmonic analysis, that all this nice, lovely Hilbert space theory plus just, hard analysis gave us a lovely theorem on Fourier series. I'm not going to reprove any of the Fourier series stuff. I'm just going to emphasize on the Hilbert space results that I just did here and how that gives you, the very famous, powerful L2 theory of Fourier series. All right, so long, take care, until next time.